Hi, welcome back. Today we are looking at section 4.2. We're going to do exponential functions. So exponential functions happen when your variable is the exponent. So you can see here I have f of x is equal to b raised to the x power. And we have to put a couple of restrictions on our base. First of all, the base has to be positive. We're not allowing any negatives. Really weird things happen if your base is negative. Feel free to go look it up. I'm sure you could find it somewhere, but we're not going to cover that here. And your base can't be 1. The base can't be 1 just because 1 to any power is 1. And that's kind of boring and not at all exponential. So that's our basic exponential function. So we're going to do a few things with them. The first thing we can do is we can evaluate them. So I have evaluate f of x equals 4 to the x when x is equal to 2. So we plug in 2, 4 squared is 16, and I'm guessing that's pretty nice. Part B here, let's do it when x is a negative half. So this one has a couple of things that I just want to kind of remind you of in case maybe you've forgotten. So we plug in the negative half, which gives us 4 to the negative 1/2 power. So the first thing I want to remind us of here is that when you have a negative exponent, it's like doing a reciprocal. So I have 1 over 4 to the positive 1/2 power. So those are the same thing. That's just something we want to remember. Negative exponents, flip it over. And then the second thing is that when you have a fraction exponent, it acts kind of like a root. So 1 over 2, that's the same as taking a square root. So we really end up here with 1 over 2. All right, next we're going to look at graphing. So I have some things that I like to see on these graphs. And we'll do a few examples too. So here we go. All right, so now we want to look at graphing. So I have a real basic example that we're going to start out with, and then we'll move in and do a more complicated one. So the example I want to start with is f of x is equal to 3 to the x. Now, if your base is bigger than 1, like we have here, you're going to end up with what's called an increasing function. So you can see my graph here real quick. It goes up from left to right. If your base is between 0 and 1, it'll go the other direction. It'll be a decreasing function. It would start at the top and then come down. All right. So when I do exponential graphs, I always want to plug in the same 3 points. Okay, and we're going to see this will work even as we make these graphs a lot weirder. But I want to plug in 0, 1, and negative 1 for x. The reason is simple. Because we have an exponential function, anything to the 0 is always 1. And the base to the first power is just the base. So in this case, 3 to the first power is 3. And if you use negative 1, you get the reciprocal of the base. So in this case, I get 1/3. And so you can see I made my graph. I have my 3 points. And that's really important because it gives us something to connect our graph to actually make the graph look really nice. That's all we need. Those 3 points is plenty to get the shape of the graph. So I have those 3 points. And then the other thing that we need to know about an exponential function is that your basic exponential function always has a horizontal asymptote at y is equal to 0. And in this case, this is a horizontal asymptote that the graph will not cross. It's never going to hit the x-axis. It's never going to come below the x-axis. Basically, that's because you can't find any power to raise 3 to that will give you 0 or a negative number. So the graph will always sit on top of the x-axis. So that's the other thing, and once we have that, we just need to know the basic shape of the curve. And what it does is it starts really flat along the horizontal asymptote. It's going to hit my 3 points that I graphed, and then it's going to grow really, really fast. And that's what makes exponential functions kind of interesting. Like I said just a minute ago, if the base was between 0 and 1, it would do the opposite. It would start really big up here, it would come down, and then it would level out and go out the right-hand side along the horizontal asymptote. So let's do one more really good example, and I'll try and throw in a lot of stuff and make it messy so you can have an idea of how to make all this work. Excuse me. All right, so here I have f of x is equal to 4 times 1/2 raised to the x plus 1 power minus 2. So this has a lot of stuff going on with it. But what we really want to do is we want to keep this as simple as we can. So I really want to continue to kind of think of this as just being 1/2 raised to a power. So if you watched my video from section 2.5 when we did, I think it was 2.5, maybe it's 2.7. Anyway, I did a video on transformation of functions. This is going to be a lot of review from there. So what we have is that the plus 1 up here with the x, since it's basically inside the function with the x, it's going to be a shift of left 1. And so what you can see is the first thing I did on my graph is I had this dotted line that I moved left 1 unit, and I'm going to basically pretend that that's my y-axis. The second thing is that I know that this minus 2 makes it go down 2. So I have another dotted line down here at y equals negative 2, and I'm going to pretend that that's my x-axis. So what I can do then is if I make my graph on the dotted lines and pretend that those are my axes, I like to call them fake axes. They're not really axes, but we kind of pretend that they are. If I make the graph there, I don't have to worry about that 1 and 2 anymore. They are basically out of my problem. And so it makes for a real nice, easy way to start the graph so that you don't have to deal with as many things at once. The last thing we have is that we do have a vertical stretch of times 4. Right, we have that 4 in front, and here's how we're going to deal with that. So I still want to plug in 0, 1, and negative 1. Now be careful, those are not really 0, 1. I mean, we're using them as 0, 1, and negative 1, but again, I'm going to be doing it with respect to my dotted lines, the fake axes that we have. So with the 4, what I want to do is I first want to ignore it. I just want to plug in 0, 1, and negative 1 into 1/2 to the x power. So if I plug in 0, anything to the 0 is 1. If I plug in 1, 1/2 to the first is a half. And if I plug in negative 1, the reciprocal of a half is a positive 2. Now I'm going to deal with that 4. Since that 4 is a vertical stretch, it's just going to multiply my y values. So what y values is it going to multiply? It's going to multiply the ones that we just found. So you can see here 1 times 4 is 4. A half times 4 would be 2, and 2 times 4 would be 8. So then the ordered pairs that I want are the first column with the last column. The middle column really doesn't count anymore. It's not going to be part of our graph. We used it to easily find these numbers over here. So now I plot 0, 4, but again, I'm going to do that on my dotted lines here. So I go to there's 0, 0. So I go up 1, 2, 3, 4. There's a dot. I have 1, 2. So I go over 1 and up 2. And then I have negative 1, 8, so I go left 1, up 8 units. There are my 3 points. You notice this time the graph starts really high, very steep, comes down, and levels out along the horizontal asymptote, which is what we would expect because our base is between 0 and 1. And so there you go. That's a much more complicated version of graphing exponential functions, and I think you'll find it to be fun. So we have some more things to look at here in this section, so hang in there. All right, a couple of things on this board. We're moving right through this section. First, the number e. E is approximately 2.71828, but it is an irrational number. It's a lot like pi. It just goes on forever, never repeats itself. It's a super important number, especially when you get to calculus. It's really fun there. But this isn't calculus, so I'll leave that alone. Along with e, we have what's called a natural exponential function, which is just f of x is equal to e to the x. Now, e is a button on your calculator, so go find it. On my TI-84, it is what I really would be looking for. It's above the ln button. So if you hit second ln, it'll give you e, and you can put a power on it. So find it on your calculator, learn to use that. It's important. All right, so now we're going to move into a few little applications of exponential functions. We're going to do compound interest. We're going to see this in 2 forms. The first is just regular compound interest, and in a few minutes we'll see continuously compounded interest. So the formula is a is equal to p times 1 plus r over n raised to the nt power. A is the amount you have after t years, or I suppose O, depends on which way you're doing this. T is time in years. P is the principal. It's the starting amount, so if you're making an investment, it's the amount that you invest. R is the interest rate as a decimal. For example, 6% needs to be 0.06. And N is the number of compoundings per year. What that is your bank will give you interest, and sometimes it'll do it monthly, which would be 12 times a year. It could do it quarterly, which would be 4 times a year. It might just do it once a year. You might just get interest annually, which would be where N would be 1. And all of those things are going to work together to change, in some way, the amount of money that you get out of your account. So we're going to go ahead and do an example, and then we'll look at continuously compounded interest. Okay, so here we have an example. We're going to start with $2,000, an 8% interest rate. We're going to do it for 20 years, and we're going to compound our money quarterly. I can read, really. So you'll see I plugged in all the numbers. There's my principal, the $2,000. There's my interest rate as a decimal, 0.08. My quarterly means that the n is 4, so I have 4 there and there. My time is 20 years. Now, I would encourage you to be very careful going through these problems. Show your work. It's really good because sometimes mistakes happen. Sometimes you hit a wrong button on your calculator, and it's really frustrating as a teacher sometimes to really know that somebody knows what they're doing and not actually have any evidence of it. So let's go through the problem. I divide the 0.08 by 4 and get 0.02. 4 times 20 gives me 80. I do my addition and get 1.02. And then be careful. You have to do the power before you can do the multiplication. This is the order of operations. So if you do 1.02 to the 80, you get 4.875 and a whole lot more numbers. I just hit then times 2,000, and I get $9,750.88. Now, I rounded it off to the second decimal place because this is money, and so we can have dollars and cents, but we certainly wouldn't want any more digits than that. So, things that affect the amount of money you get out of this, obviously the higher your interest rate, the better. There's kind of a limit. You're not really going to get interest rates that are too much higher than like 11 or 12%. The amount of money you invest is going to, change how much you have at the end. But again, unless you've got way more money than I do, it might be hard to even come up with $2,000 to invest. The number of compoundings makes a difference, but maybe not as big as we think. It's really the length of time that makes all the difference in the world. So, I like to tell my students, start investing early because it will pay off in the end. So let's go ahead and move on to continuously compounding interest, and we'll see how that changes things. All right, finally we have what's called continuously compounded interest. I'm going to do the same problem, except I'm going to change my compounding from quarterly to continuously. So we still have the same principal, the same interest rate, the same length of time. What does change, though, also is the formula that we're going to use. Okay, continuously compounded interest doesn't have an n, but it does have an e. So the formula is a is equal to p times e raised to the rt power. So I plug in those numbers, the 2,000 for the principal, the 0.08 still a decimal for the interest rate, 0.08 times 20. And again, I'm going to be careful and follow the order of operations. 0.08 times 20 is 1.6. When I do e to the 1.6 power, I get 4.9 and a whole lot more numbers. So I just hit times 2,000, which gives me $9,906.06. Which, if you go back, that's a little bit more than what you had from the compounding quarterly, and that's to be expected. You're getting interest more often, but it doesn't make you rich. So there you go. That's compound interest. Make sure you know both formulas. They're both very, very useful. And have a great day.